In 6.3, we're going to look at exponential relationships. We're going to look at exponential functions as graphs. We're going to look at exponential equations. There's a whole lot packed into this. Now, a lot of this is review, but this is a really intense section. And so the first thing we're going to start with is some basic exponent laws. And I'm going to start by writing this out a little bit like the textbook does it, but know that we're going to talk about it in a little bit more detail. We have a base of a raised to a power. So a to the power of s times a to the power of t is equal to a to the power of s plus t. To give context to this, if I have 2 to the third power times 2 to the fifth power, this is 2 to the 3 plus 5 power, or 2 to the 8th power. But let's look at y. If I were to write these two numbers, 2 to the third power, 2 to the fifth power, in their expanded form, it might look like this. It's like saying 2 times 2 times 2, that's 2 to the third power, multiplied by 2 times 2 times 2 times 2 times 2, that is 2 to the fifth power. But when I'm multiplying all of these up, the question is, how many 2's do I have? And I have 1, 2, 3, 4, 5, 6, 7, 8. So when we're multiplying two numbers that have the same base, if we think about them in their expanded form, I think of it like an accordion. If I accordion all of this out, I can see all 8 of them. It's 2 to the 8th power. So what we're saying is I have 3 of them right here, and I got 5 of them right here. Collectively, I'm going to have 8 of them, or 3 plus 5 of them, all multiply together. So that's 2 to the 8th power. Next, if I have I'm going to use black to be consistent, a to the power of s, and then all of that to the power of t, that is a to the power of s times t. So to give context to this, if I have 3 to the 4th power, and then I raise that to the 3rd power, according to this, that is 3 to the power of 4 times 3, or 3 to the 12th power. But once again, let's look at y. 3 to the 4th power is 1, 2, 3, 4 3's all multiplied together. And what I have is that cubed. I have this cubed, or this times itself 3 times. So once, twice, 3 times. And if I look, I can simply count those up. That is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I have 3 groups of 4. 3 groups of 4, or 3 times 4, 4 times 3, which gives me altogether 12 3's being multiplied by themselves. So when we have powers on top of powers, ultimately, we can write them all out to see it, but ultimately it's just going to be this 3 to the 4th power that many times, or 3 times 4 3's. It's 12 3's written right there. Next, if I have 2 things being multiplied together, a times b to the power of s, that is equivalent to a times s, a to the power of s times b to the power of s. So if I have 2x to the 3rd power, that's 2x times itself 3 times, 2x times 2x times 2x. And this gives us how many 2's are there? And the answer is, well, there's 3 of them. How many x's are there? Well, there's 3 of them. I sometimes think about this as distributing that exponent. So remember, this is 2 to the power of 1 and x to the power of 1. It's going to be 3 times that. It's going to be 3 times that. Real common mistake people make is people usually remember to do the x. They're like, oh yeah, that's going to be x cubed. But a lot of times people forget that you also have to cube the coefficient out front. So make sure that you cube everything in there if there are multiple parts, including that coefficient, because it's definitely wrong if you don't. Next thing we're going to look at, 1 to the power of whatever. 1 to the power of s equals 1. Now, s is a variable. It could be anything. It could be 1 to the power of 4. It could be 1 to the power of 16. It could be 1 to the power of 137. 1 multiplied by itself any number of times will always be 1. And that includes if it has negative values, negative exponents. So real quick, let's talk about negative exponents. So if I have something like a to the negative n power, the textbook says that is 1 over a to the power of n, or 1 over a to the n power. Now, these three all mean the same thing. But what you have to understand here is there will be moments when it's convenient to look at it like this. There will be moments when it's convenient to look at it like this, something you need to be familiar with. Now, why is it that a to the power of negative n equals 1 over a to the n power? So let's start here. If I have 5 to the third power and 5 to the second power and 5 to the first power, well, 5 to the third power means 5 times 5 times 5, which is 125. 5 squared is 5 times 5, which is 25. 5 to the power of 1 as well is just 5, and it's just 5. But if you look here, as we reduce the number of 5s being multiplied, when you look at the final answer, it's like divided by 5. And that's divided by 5. So hopefully then it makes sense to you that when I say 5 to the 0 power, it follows the same pattern. Divided by 5, and it's divided by 5. Well, 5 divided by 5 is 1. 5 to the 0 power, or more generally, a to the 0 power, will always equal 1. So long as a doesn't equal 0, 0 to the 0 power gets a little weird, but ultimately, any number to the 0 power equals 1. And we can see that by simply dividing by 5, dividing by 5. So the real question is, what about negative exponents? Well, the pattern continues. We still divide by 5. So 1 divided by 5 is literally 1 divided by 5. It's 1/5. If I have 5 to the negative 2 power, I once again divide by 5. And that's 1 over 25, or we could say that's 1 over 5 squared. 5 to the negative third power is 1 over 125, or 1 over 5 cubed. So what you'll notice is there's perfect symmetry. You have the positive versions, this right here, the positive versions. And then when you have the negative versions, it is just the multiplicative inverse. It's just 1 over those values. 1 over 5 to the first power. 5 to the negative 2 power is 1 over 5 squared. 5 to the negative 3 power is 1 over 5 cubed. There's perfect symmetry. There's perfect symmetry between the positive and negative versions of those. So a to the power of negative n is 1 over a to that power. It flips the bottom and becomes positive. And you can also look at it as 1 over a to the power of n, because 1 over n is just going to be 1. Different ways of approaching that. So those are your basic exponent laws. There are tons of YouTube videos that talk those out in greater. If you want to talk to me on WebEx, please reach out. But we're going to use the heck out of these properties in the coming videos.